Good morning. Let's start with the first talk by Kimyeong from Korean Institute of Advanced Studies.
All right. So first of all, I would like organizers for giving me opportunity to talk about what we have done recently. So I'll talk about the works I have done with my three collaborators: Hirotaka Hayashi in Tokai University, Seong-suk Kim and Futoshi Yagi. Both of them are in Chengdu, China. Uh, So first, we heard briefly about 5D conformal field theories from Antonio on Monday, and Ricardo touched it a little bit yesterday. So let me start with how one can get the 5D gauge theories from 5-brain webs and how it leads to superconformal field theory. So 5D supersymmetric field theory with 8 supercharges can appear as a world volume theory on 5 brains. For example, one can have a PPS 5-brain webs made of T5 brains, O5 planes, or NS5 brains, and PQ5 brains, and one can have also 7 brains, filling the 1, 2, 3, 4, and 7, 8, 9 directions. And the webs will live on a plane or 5, 6 plane coordinate. So for example, if we think about SU2 gauge theory without any matter field, then there are two kinds of theories, discrete theta term 0 or pi. Depending on these two discrete thetas, so one can have this kind of webs. So this is for theta equal to 0, and this is, for example, theta equal to pi. Now, this PQ5 brain webs are structured so that tension is balanced. So if, for example, PQ5 brain will have a tilted with a slope given by Q over P. Now, 5D Yang-Mills theories, if you look at it, is non-renormalizable as coupling constant square has one over mass dimensions. So that and this theory is very weakly coupled in IR and is very strongly coupled in UV. And I don't think we have done any analysis, but one assumes there is no Landau pole. So theory is non-renormalizable, which means it's not well-defined UV. So for a long time, I guess people haven't studied much of these theories, as you cannot have any fundamental definitions. But people have been finding out that this theory can be well-defined in UV by some conformal field theories, especially that theory, conformal field theory can obtained by taking coupling constant to infinite. So once you take a coupling constant, which has a dimension per parameter, goes to infinite, then there's no dimension per parameter, because infinite is, you cannot scale the infinite to any finite value. So theory becomes conformal. And so question is whether there's such a theory exists. And it turns out interesting question is, of course, without supersymmetry, whether such theory exists. And but at least for the supersymmetry case, people found that there is a constant UV convolution of these 5D n equal 1 supersymmetry Yang-Mills theories, and that UV convolution is given in terms of some sort of superconformal field theory. That's what Seiberg has proposed about 20 years ago, inspired by strings theory. Now, this conformal field theory in 5D has, this theory can exist only with H supersymmetries, and the conformal symmetry has been found by Won and Am is 40 years ago. And this 5D conformal field theory with SU2R symmetry is called F4, is the exceptional group. If you have more supersymmetries, then this 5D Yang-Mills theory can be completed in 6D theory, not in 5D, about which I will not talk much about. So 5-brain webs for in type 2B has been studied quite extensively to find out these 5D superconformal field theories. And these webs provide us non-perturbative aspect of the theories and also allow us to develop some sort of topological vortex calculations which captures the BPS object of the theories. And one of the key interesting aspects of this 5D conformal field theory is that one can have some classical flavor symmetry coming from the number of flavors. And then there's an instanton, BPS instanton object, which arises from Yang-Mills theories. And so those are two global symmetries. But as superconformal point, as Cyborg argued, that for SU2 case, for example, these two classical group and this non-perturbative U1 global symmetry merge into exceptional global symmetry, which is characterized by number of flavor plus 1. So for example, 5D n equal 1 SU2 gauge theory with 5 flavors. So matter in hypermultiples in fundamental representation, 5 of them. Then there is SO10 global symmetry as SU2 is pseudo real. And then there's U1 global symmetry from instantons. So together one has have in superconformal limit E6 enhanced global symmetries. So for example, NF equal to 0 case with theta equal to 0, E1 case, there's only global instanton U1 symmetry from instantons, but this is enhanced to SU2 global symmetry. So about the reason this SU2 enhancement of global symmetry comes from the S duality, which we heard from Antonio. So if you look at the map, I mean waves for fibrine waves for SU2 gauge theory without any flavors, then there's D fibrine and S fibrines, and then there's fundamental string connecting D fibrines are W bosons, and D strings connecting S fibrines are instantons. And this theory is invariant on the 90-degree rotation, which is S dualities. What boils down to is that so you have matrix U1 gauge theory living in this Coulomb phase of conformal symmetry. Conformal theory where this matrix U1 symmetry scalar part of vector multiply is basically vibration of this box. And then this U1 gauge theory either live on D fibrine or NS fibrines, but they describe the same object. And in 4D, if you have two, one is electric and one is magnetic in some sense, and if we have electromagnetic dualities, then we have this natural transformation using epsilon tensors. But in 5D, this transformation between two photons, which describes same physics, is non-local. And I don't think anybody really studied the exact nature of dualities between two descriptions of photons. But there's only a single kind of photons living there. But there are two kinds of W bosons, one coming from the fundamental string, one comes from instantons. And this SU2 global symmetry has phi symmetry, which is exchanging basically fundamental string with these strings. So it's a very non-local, in some sense, global symmetry, because instantons are non-local in terms of SU2 gauge theories. So this theory in Coulomb, if you look at the Kuppakuma alpha invariance partition function we heard from the Ricardo, then there's one massive vector multiplet, but there are two massive vector multiplets, one W boson and the instantons, and mutually non-local to each other. So this is a complete different sort of S duality than 4D physics, where we have monopoles and W bosons, but basically those are same object. I mean, you have single D3 brane, then you have so here D3 branes, then fundamental string and D strings connecting same D3 branes, but here D5 branes and S5 branes are related by S dualities. Yeah.
Is that SU2 over there, does it correspond to the R symmetry of F4 when you are in the infinite coupling limit?
No, that's nothing to do with that. SU2 R symmetry. This SU2 is, remember I said 5 flavor is E6. So 0 flavor is U1 instantaneous to SU2. So it's global symmetry, not part of the supersymmetries.
Okay, thank you.
Now, so for example, this wave diagram for SU3 gauge theory is Chern-Simons level 0, 1, 2, 3. So as you increase the Chern-Simons levels, then you can see some of lines are coming together, and 4 will be colliding each other, 5 will be more severe. So you can see the drawing waves for higher Chern-Simons level is more difficult.
You were mentioning discrete theta angles.
Right.
Are they the same as the discrete theta angles? Are the same as the Chern-Simons levels in this talk? Or?
No, discrete theta angle arises for SPN gauge groups, where the pi 4 over SPN is Z2. And so especially this discrete theta angle, when you have flavor, you can change it. So there's no meaning of discrete theta angle.
Okay, then for SU2, SU2 can be also regarded as SP, right? SU2
Yeah.
can also be regarded as
SSP1, right.
So in that case,
You have discrete theta when there's no flavors, but with flavor, there's discrete theta can be changed from 0 to 2 pi.
okay, and in the case of
That's
SU2, is the discrete theta angle different from the Chern-Simons level?
Yeah, I mean, right, SPN theory doesn't have Chern-Simons levels.
Mm-hmm. Okay.
So
Because from the wave diagram, they seem to be related, but okay.
Right, so... Right, so yeah, they are sort of related from wave diagram because it's bending of the waves, but from gauge theory, they are completely different objects.
Okay.
So now having this wave diagram, you would ask, how do you identify Chern-Simons level from this wave diagram? And the simplest way to identify Chern-Simons level is by calculating free potential of the theory. So free potential is basically like in n equal 2 theory in 4D, but in 5D, free potential is finite and is just determined up to cubic. There are only cubic term in Coulomb parameters. And the free potential is made of 3 pieces, and 4 pieces, I guess. There's a quadratic term coming from the free Lagrangian Maxwell terms, and then there is a Chern-Simons level arising for SVN gauge theory, but not in other gauge groups. And then there is one loop correction coming from the, remember in 4D, n equal 2 theory has a one loop correction plus all the instant corrections, but in 5D, there's only one loop corrections. And so this one loop corrections are made of the W boson contribution plus meta multiple contributions, and they come with opposite sign, and meta multiple contribution, of course, depending on their mass terms. Now, so that's a free potential then from which one can take a derivative of free potential. First derivative will give us monopole tensions, and two derivative of free potential leads to coupling constant, effective coupling constant. Now, this magnetic monopole, if in 4D theory, there are charged particles and magnetic monopole particles. In 5D, even though you have charged particles, the monopoles becomes strings. So monopoles are like D3 branes, for example, covering this web, this face of this 55 brane webs. So you spend 2 dimensions on the web, then you have one remaining direction, which is monopole string. And monopole string tension is given in terms of first derivative of these free potentials. And it's depending on the not only flavors, also depending on Chern-Simons levels. So SU2 gauge theory, for example, there are 3 Coulomb parameters whose sum is equal to 0, and then one can parameterize Coulomb parameter in natural way, and then derivative of phi 1 generate a tension of this monopole string, and the derivative is phi 2 generate this monopole string, and then you can calculate this area using the 55 brane webs, and then compare with the free potential, and then you can indeed see that this Chern-Simons level, which is integer for without meta flavor, and half integer if the number of meta flavor is odd numbers, and then you can identify this web's Chern-Simons level exactly from this free potential calculation and area calculations. Now, so for example, SU2N theory with pure SU2N theory, one can bend the boundary peak fibrine webs, increase the Chern-Simons levels. Then, when Chern-Simons level is very large, you have this plops, and then beyond that, it's very hard to draw. So, challenge is to how to draw peak fibrine webs in higher Chern-Simons levels. And turns out that's part of my story, but there are many interesting stories behind it. So small Chern-Simons level you can generate by n parallel D fibrines between 2 and S fibrines. Then that's what I did. And also one can introduce orientifold like O5 plane. Then you can introduce into peak fibrine. Then one can get the USP2N gauge theory or SO2N or SON 2N plus 1 gauge series. So 5D, so SU2 rank 1 superconformal field theory has been classified by Cyborg and his collaborators. Now higher rank theories. So how many rank means number of Coulomb parameters, independent Coulomb parameters. And recently this group of people have classified for rank 2 cases where number of using the shrink of Calabi-Yau threefold. And it is, even though written by half of them are physicists, or more than half of them are physicists, it is very mathematical. And having brain pictures leads to much clearer picture of the theories, and also it allows us to calculate, for example, using topological vortex method, calculate the instanton effect. So that's a kind of challenge we took and then achieved some goals. Right. So, for example, we did fibrine webs to 2 applications for low rank. So rank 2 cases, we found all the brain webs, and the brain webs are extremely powerful to let us test the duality between different gauge group theories. So, for example, suppose you have a different gauge group, and then in 5D conformal field theories, UV physics. So in 4D, for example, Cyborg dualities, you have different UV descriptions, but you get same IR infrared conformal field theory. Something similar. Here you have 2 different kind of IR gauge theories, but UV conformal field theories are identical. So those are some sort of dualities which I will talk about.
Is everything that was in Katz and Vafa et al.
Yeah.
That also reproduced in the brainwebs?
Yeah.
Okay. So
Yeah. So and also we are working on higher ranks, and we made some progress. But I hope I don't think I have time for that. Right. So this I guess I did the best resolution, but somehow. Right. So this is sort of rank 2 theories, and we have all the web diagram, and there are some missing parts in the diagram, so we corrected it. And right. So so let me start this 5-brain webs for G2 gauge groups. Then I'll talk about G2 SU7 dualities. So both theories are very different IR, but UV superconformal field theories are identical. And then I'll do more refined cases. So for G2 gauge group, as I said, SUN gauge theory can be obtained easily. Now SON theory can be done using orientifold. Now G2 gauge group is an exceptional group, and it seems like very hard to get it from brain webs. But the way we get it is we start with the SO7 gauge theory, and then we introduce spinometer field. Then we use the Higgsing the spinometer field, which SO7 spinor is 8-dimensional, and you fix one of the directions of spinors, then one generates the G2 gauge theory. And I guess we heard some octonions, but this is also related to octonions. Octonions and gauge group G2 and SO7 are SO8, all of them are intimately related to each other. Or one can start with SO8 gauge series, then one can get the SO7 either using vectors or spinors because of triarities. Then we can get a different sort of SO7 gauge series. Then Higgsing one more time generate the G2 gauge series. So we have two kinds of waves for G2 series. They look very different from each other. So we start with O5 planes, and which describe SO7 or SO8 gauge groups. Right. So let's think about. So there are. We know well that there are four kinds of O5 planes: O5 plus, O5 plus tilde generate the USP2N gauge series. O5 minus generate SO2N. O5 minus tilde generate SO2N plus 1. And then there is a OM plane, which is SGL version of the O5 planes, which will play some role also. So let's start this pure SO7 gauge series. We have O5 tilde planes, and then there are three T5 range generate rank 3 gauge groups. And because O5 minus tilde has half T5 range, the fundamental string ends here. And so it gives you a short root of the SO7. So this is the SO7 gauge theory. Gabi has introduced the spinor method on SO7. The way he introduced SO7 spinor method is by introducing another 1-1 planes here. I think it is. And what happens is that theory living on it is USP0 gauge theory, so there is no gauge theory. But still, one can introduce D1 strings connecting this 1-1 planes and this minus 2-1 planes. And then these D1 strings, one can imagine there is D5 range, then there is a pi fundamental method connecting SO7 is USPN series. Then there is a general mode of the pi fundamental method on D1 strings. And they are instantons of USP0 series. So D1 strings USP0 instantons, then this general mode generates spinor method of D5 SO7 gauge series. So this is the way to generate the spinor methods. So once we have this brane, then we have a spinor method. And then when we have spinor method, one can see that there is a SU2 global symmetry because these two branes are parallel to each other. And the spinor method mass term is the distance between these 1-1 branes. So to Higgsing it, we have to introduce this mass term to 0. So we have to pull the spinor method to these directions. Then we have to Higgs it because you can go to Higgs mechanism only when spinor method or method field is massless. So one has to do the flaps, and fortunately we have done previous work where when we have oriented for what kind of flap one can have at this point. And so using these flaps, we can make a transition and pulling this 1-1 brane further to this limit where the spinor method becomes massless. So we did one flaps, and then do another flaps, and another flaps. So then one has to do massless limits. So best parameter to be 0. And then we have one NS 1-1 brane ending here. Then there are two 1-1 brane ending on 2-7 branes. So you can terminate the 5 branes on 7 branes. And once you do that, then you can do the Hanai-Witten. And this 1-1 brane can jump the disjoint and they're ending up there. So and then both of them are so the fermionic branes on this 7 branes, but because their starting point is different, they can end on the same 7 branes, and because both of them ending on the same 7 branes, so we can pull out this interval 7 branes outside. That's the Higgsing. So what Higgsing means is that you are freezing by having a method spinor method to have non-zero expectation values, And from wave diagrams, you are freezing the degrees of freedom. So you are reducing the rank of the gauge group from SO7 to G2. So, so after Higgsing, this is the 5-brane wave for pure G2 gauge series. And then you would ask, how do you know this G2 gauge group? And again, prepotential is extremely convenient tool to generate, to feel comfortable about this wave is for G2 diagrams, because one can start this prepotential for SO7, then one can follow the Higgsing through the whole prepotentials. But one can start directly with writing down prepotential for G2s, and then there's two independent Coulomb parameters. Initially, SO7 is rank 3, but this is rank 2. So there are two independent Coulomb parameters. Then one naturally can introduce phi 1 and phi 2 bases. And then with that prepotential, one can take first order derivative, then one can get monopole tensions, T1 and T2. Now, so again, magnetic monopole string is made of the T3 brane covering these faces. But this looks like there are 4 faces, but there are only 2 monopole strings. And it turns out the way one can identify is that, for example, there are 2. One of them is made of the T3 brane covering this face, and just A gives T1. And because of Coulomb parameters all locked each other, second monopole string tension is made of the B area of this one plus the area of that plus twice the area of this. And the reason we have twice the area of this is that if you go back, remember we started with SO7, and if you go to 4D theories, then electric charge have short root, and dual magnetic charge is a long root. So magnetic charge is twice the length of the electric charge. That's why you have twice the area of these. And then if you calculate this area from these wave diagrams, then of course, you can do it in 5 dimensions too.
It's just the root.
Yeah, it's just a root of it. Yeah, right. Of course. Right. So naturally, from this prepotential, you can calculate, from this coordinate, you can calculate the areas, and then you can compare it, and indeed, this T1, T2 is given in terms of this. T1 is A, and T2 is given in terms of this summation. So this confirms again, then this is the theory for G2.
So can I ask, what does it correspond to just have a D3 brane, say, covering C? If it's not?
Because just D3 brane, that's not consistent in the sense that brain physics is much more delicate, but through the Higgsing process, you are covering just part of it. Then when you do Higgsing, I think, remember when you do magnetic charge with Higgsing, there's flux going out, and then that becomes inconsistent. So you have to some more of that. Then only with that, this configuration is consistent. Right, so we have now a wave diagram for G2 gauge series. Now let's look at duality between G2 and SU3 dualities. So this duality has been proposed by these people just from the symmetric considerations. But it's a bit mysterious. As I said, SU3 theory with higher Chern-Simons level is very difficult to draw. But now from wave diagram, it looks like almost trivial. So here's a pure G2 gauge series. Then we do S dualities, which is 90-degree rotations. Then O5 tilde becomes ON tilde. And then there's this diagram where there are 3 parallel lines, which is for SO7 now is locked. So it's a SU in G2. Now, if you rotate it, then we have 3 parallel lines. It looks like SU3. Now, then you could say, how do you know this is SU3? And how do you know it's SU3 is Chern-Simons level 7? And one can do the same thing. I wrote down the prepotential for SU3. ON tildes? So ON tilde is a little more delicate. Originally, ON0 was discovered, which is has a weakly coupled description. ON0 means is that O5 minus is 1D5, then you S dually, then you have ON0, then you have a D5, NS5 range and T5 range, then you get a T-type quivers. So probably late 90s, early people are trying to find the T-type quivers using brain pictures, and the ON0 was the T-type quivers. Now ON tilde and the OM can be naturally imagined by Higgsing the say ON0 with other things. Then you can go to Higgsing, then you can go to different type of quivers. I mean, because you do the Higgsing in get the tilde variables, you do Higgsing in O5 minus. And then you can imagine the same sort of thing with ON0, then you get the ON tildes. And then, so I'm saying that there's a single superconformal field theory, then I can do the, because 5D Yang-Mills theory is a relevant deformation of the theories. There are two relevant deformations, one with G2 gauge group, another one is SU3 with Chern-Simons level 7. Same theory, right? Oh, that's a coupling constant. Because remember, UV theory. Yeah, that's one parameter, but they are residual to each other, means they are non-local to each other. No, there's one mass parameter. So let me tell you. So basically, what happens is that if you do positive mass deformation, then you get a say G2. If you do negative mass deformation, then you get SO7. SO3 is Chern-Simons level 7, right? So it's a coupling constant changing the signs. Right, so the way one can identify SU3 Chern-Simons level 7 is, again, you give a coordinate, then you do prepotentials, and then you look at the areas. Let's see. And then, right, then you do areas, then basically this, so now this, you have to do 90-degree rotation, but again, monopole mass comes out the same way. And then you can see that only with Chern-Simons level 7, they generate the same monopole tension. So you can see they are the same theories. So interesting thing is that, as I say, if you go to conformal limit, then when you do coupling deformations, when you do residual transformation, coupling constant to change the sign. So cubic potential so again, cubic prepotential has to be extremely powerful. It's made of 3 contribution, then Chern-Simons contribution for SUN theories. G2 doesn't have Chern-Simons terms. And then there's one new contribution from W bosons and flavor symmetries. This one comes from W boson only, but somehow it captures all the S-dual physics in there, which is again rather mysterious. Remember, there was in SU2 case, either we have a W boson or instantons, both of them are vector bosons, but in one loop, and they are non-local to each other, but one loop we just do W boson, and that captures all the wave diagram physics, so non-perturbative physics. So, and also monopole tension is given by first order derivative, and coupling is given in 2 derivatives. So when Intelligate and Morris and Seiberg studied the 5D conformal field theories, they require the coupling constant to be positive definite. But people found that there are more theories have superconformal theory which violates this constraint, and that has been improved by this gentleman, that all the Coulomb, this is theory is acceptable if the positivity of monopole tension is acceptable, so that theory constraint become milder. and that allows us to people to explore more possible theories. So if you look at the dualities, then you can see that parameter mapping, SU3 coupling constant and the G2 coupling constant has opposite signs. And then one can identify all the parameters. So, so we confirm the dualities, and the monopole string is given in terms of face of the diagrams. And then you wonder what happens. So kappa equal to 2 cases. I drew the Chern-Simons level 4 cases. Now I drew the 7 cases, but you can draw the Chern-Simons level 5. That's the SU3 theory with Chern-Simons level 5. Now you can see that by introducing oriented fold, we jumped the Chern-Simons level to 7. One of the reasons is that monopole mass got doubled here. And by increasing Chern-Simons level means we need monopole tensions. So this allows us to another directions. If you look at the list of these theories, then they have a theory with SU3 theory with Chern-Simons level 9. And that's marginal theory. And we found a brainwave for that by just introducing 2 oriented fold. So once we have this oriented fold, then the monopole mass will be 1, it will be given in terms of area of this. And another will be twice of this, plus twice of that, plus some of this. So monopole area has been increased. And this theory turns out to be Chern-Simons level 9. And this theory was constructed geometrically, but brainwaves we constructed it very nicely. Interesting thing is now because we have 2 brainwaves, this theory is 6-dimensional theories. And turns out that, I guess, Kabi and Radama probably, they argue that this SU3 theory with Chern-Simons level 9 comes from 6D theory with SU3. Among all the 61 theories, there is a SU3 gauge theory with a tensor field and no matter field. And when you compactify the theory on a circle with a twisting, you get these theories. Right, so I talked about monopole tensions. Now let's go over to some rank 2 theories, which I showed you before. So among which there's an interesting correspondence between, not only between G2 and SU3, one can have G2, SU3, and SP2 sequences. So in this case, there are single superconformal free theory, but there are 3 deformations. So SU3 and the SP2 duality has been studied before, but now G2 is there, so 3 of them are all related to each other. So for example, for this triality, one has to think about G2 gauge group with, say, 2 flavors, and which can be obtained from SO7 is 3 spinors. Then Hicksing it, we end up with G2 with 2 spinors with 2 singlets. So this is the wave diagram for G. So one studies SO7. Here is Hicksing. So we have a G2 is 2 flavors. And one can identify pair couplings, and one can create prepotentials, and one can calculate the monopole mass, monopole tensions. For example, there's one monopole coming from the middle face, and then another monopole comes from face of this, face of that, twice of face of 4, and the face of 5. So that will be a sort of monopole tension for G2 2 flavors. One can do a S-dual transformation with ON planes, and that should be related to SU3 theory. But even though one can see SU3, it is too complicated to make it SU3. Turns out one can, as of warming up, for example, SU3 is Chern-Simons level -1 with SU2 gauge theory. So these are quiver theories. One can Higgs the SU2 quivers gauge groups using fine tuning. Then that generate one antisymmetric hyper plus level change of Chern-Simons level by 3/2. And then one antisymmetric hyper of SU3 theory is similar to fundamental method, and one can do the flops to generate this theory after Higgsing is identical to SU3 with 1/2 Chern-Simons level with 1 fundamental. Key lesson is by introducing SU2 and Hicksing it, we change the Chern-Simons level by 3/2. So to get SU3 Chern-Simons level 6 with 2 flavors, one studies SU2, SU3, Chern-Simons level 3, and SU2. So there's this like D-type quiver. There are 2 SU2s living on it. Then there is SU3. Usually D-type quiver will be SU2, SU2, and SU4. But we Higgs this part of the story so that we have SU3 Chern-Simons level 3. And then we Higgs this 2 part of the SU2s independently. By Higgsing it, then we end up with, because each one of them, SU2 generates Chern-Simons level by 3/2, so it increases Chern-Simons level to 6, and it generates 2 antisymmetric hypers. And
which method do you use in order to compute the level of the Chern-Simons in a product setting?
For this setting?
Yeah. So in the previous slide, you also had the level
Right.
1/2, and so which method do you use to compute the level?
Which?
-1 and 1/2.
Oh, you mean how do I get it?
Yeah.
Oh, so right. So you wonder why this is -1, depending on how I put SU2. So I have to decouple SU2 to SU3. So you have to split them. Then you look at the
And then see what you
right.
I see.
So once you can see this case, this diagram is identical to G2 with 2 flavors. So you can see G2 is 2 flavors as dual to SU3 with 2 flavors. And then we want to argue that's equivalent to SP2 with Chern-Simons level pi with 2 antisymmetric hypers. Now, I told you that SPN theory with meta field doesn't have discrete zeta terms. That's true only for fundamental representation, but if you have antisymmetric representation, then still you can have discrete zeta terms. So, so the way you get this theory is starting from the SU3 with 2 antisymmetric hypers. Then you have this double lines and then single lines. And then you do flop by attaching 7 branes, so you can do the flops. And then, so you're bringing in. And then you have to pull out in different directions. So you do bring it, there are cuts, and then you have to bring it, change the directions. And then you pull them out. This is the diagram. But again, this can be regarded as, again, this part is basically, if you pull them in, then this like O7 minus, you can merge this 7 brane to O7 minus, and this part is periodic, so this goes like this, because they are identified along the O7 minus, then you split O7 minus into 2 7 branes, then you pull out, and this is the diagram. And once you have O7 minus, then this web can be regarded as SP2 theory, and with 2 antisymmetric hyper. Again, this can be identified using prepotentials. So then one can add more meta field, and it turns out that G2 with 6 flavors is equivalent to SU3 with Chern-Simons level 4 and 6 flavors, and which is equivalent to the SP2 is 2 antisymmetric hyper and 4 fundamentals. And one can go from one theory to another.
So can I ask Matt's
Yeah.
question again? So so now that it's triality,
Right.
now how do I deform from the SCFT point?
So you have to look at the parameters and see how.
But
because-
how many are there? Or
Well, there are mass parameters and coupling constant.
oh,
And-
so there's more than one.
right. So here's the relation between SP2 and G2. So they have comes with same signs. Now, if you look at the SU3, then it's very delicate. So SU3 case, you have this M0 is bare coupling. Depending on the beta multiplet, and then there's mass parameters playing all kind of roles. So it's not nice triality. You can see there are three gauge groups are very different characters, so the relation between them should be rather complicated. And so those are the relation between mass parameters and Coulomb parameters. So turns out that it's not triality. There is one more theory, which is SO5 with two vectors, and SO5 is SP2, of course. So antisymmetric hyper of the SP2 is two vectors, and the four fundamental is four spinors. From brainwaves, you can again draw different diagram for SO5, and this is the SO5 diagram, so one can make a flaps, and you go to these pictures also. And this theory is expected to be obtained from twisting of 60 SU3 with tensor and 12 flavors. By twisting, you reduce the rank and also reduce the flavor by half. Now, there's other kind of dualities. For example, SU3, tensor level 0 is one fundamental and one symmetric. This is not the duality. This is another marginal theories. So let me draw this marginal theory starting from SU3 0 with one fundamental and one symmetric hyper. The way to introduce symmetric hyper is by, this is done by Gavi Charfeo and Oren Bergman, introducing how to introduce symmetric methods. So one has to start this O7 plus. Then there is identification of the distraction. So this 5-brane, 1-on-5 brane goes around the orientifold plane, then it becomes the -4 1 planes. And then NS5 brane ending on the O7 plus, 1-on plane ending on it, that generates symmetric hypers. So here's SU3 gauge group comes from, there's 3 parallel lines, so there's a W boson like that, then W boson like that, so there's SU3 gauge groups. Then one fundamental comes from there. So this theory is supposed to be marginal theory, which means it should be 60 theories. And the way one can get, so before talking about marginality, one can think about the decoupling of the theories. Either you can decouple this fundamental method to infinite, and then we get the SU3 minus 1/2 tensor level with one symmetric hyper, or one can decouple the symmetric method, and then we end up with SU3 tensor level minus 3/2, 7/2 plus 1 fundamentals. So how do you know this one has one symmetric and one fundamental meta field? By, again, looking at the prepotentials. So for example, you have O7 minus, then you drew the mirror diagrams below, then there are 3 Coulomb parameters. And then using the prepotential, one can calculate the prepotential is determined by W bosons and the meta field. So one has to include the symmetric meta contributions. And once you do that, one can compare with the suitable mass parameters. In this case, we choose mass parameters like that. Then one can compare the area of 1 and 2 and compare the area coming from prepotential, and they are identical to each other. So one can indeed see that this web is for SU3, one fundamental and one symmetric hypers. And the SUN case can be just draw more lines. And marginality can be seen, I guess I didn't introduce, but by introducing another 7 brane, O7 minus, then together O7 plus and O7 minus is the one which tells us that this is indeed a 60 theory. So in final lot, for example, SP2 theory is 1 antisymmetric hyper and 8 fundamental is equivalent to the SU3 with tensor level 3/2 and 9 fundamental meta field. This SP2 is 1 antisymmetric and 8 fundamental arise from the, suppose we have in heterodyc string theory, we have E8 branes, E8 walls. Then suppose we have a single M5 branes, then that's 60 E8 string theory, where there's one tensor mode with hypermultiplet living on the E8 walls. But if we circle compactify on a circle, then this 6D theory becomes 5D theory, where SU2 gauge group is 8 flavors. Now, if you have two M5 branes, then again, still EA string theories. If we compactify on a circle, then we get SP2 gauge theory with one antisymmetric hyper, which tells about relative position of two M5 branes, and then a fundamental meta field. Now, this theory turns out to be equivalent to SU3 gauge theory with Chern-Simons level 3 half and 9 flavors. To see that, one can do the warming up with SU3 Chern-Simons level 5 half with 7 flavors. We want to say is SU2 is Chern-Simons discrete set atom pi, which is 0, and then 2 antisymmetric hyper this typo plus 5 fundamentals. So this SU3 5 half with 7 flavors. This is the wave diagrams. We make S dualities. We do a lot of flops and moving the 7 branes around. This previous step. So this is the SU2 pi with Kiva theory with another SU2 is 5 flavors. So we end up with these Kiva theories. And then, for example, again, we have to do a lot of exercise. SP2 is 2 antisymmetric hyper, and 4 fundamental. One can decouple, and then we get SP2 is 1 antisymmetric and 4 fundamentals. So you can see this sort of waves. And so that exercise tells us how we get SP2 is 1 antisymmetric is 4 fundamental, and the SU3 is Chern-Simons level 3 half is 5 fundamental. You can do all kind of the web drawings. And then we can do the real stuff, which is SP2 is 1 antisymmetric and 8 fundamental is equivalent to SU3 3 half with 9 fundamental. So this is the wave diagram for SP2 with 1 antisymmetric and 8 fundamental. So to convince this right diagram, you have to do the case where flavor is much smaller. Then you play around, and then you go to the marginal theories, and then indeed we can move around, and we can show that this theory is equivalent to SU3, Chern-Simons level 3 half with 9 flavors. And I talked about SPN with 1 8 fundamental and 1 antisymmetric hyper, which is basically E8 wall. It's a type 2-1 picture of the E8 wall with M5 branes. And so to conclude, we recovered all the 55 brane wave for rank 2 theories, and we showed the duality between different theories in Coulomb phases. We made some progress in exceptional cases of higher rank, including rank 3 antisymmetric tensors, which is not present in 6D theories, but somehow by you go to 5D theories, one has to generate rank 3 antisymmetric tensors for, say, SU6 gauge groups, for example. And it will appear soon. And there are a lot more challenges remain. And to me, the most interesting challenge is that UV completion of the theory. Remember, we started with 5D gauge theories, which is non-normalizable, but somehow there is a UV fixed point, which is very well defined. And then superconformal theory, and then one can do a lot of calculations of that theory. But as a perturbative sense, theory is non-normalizable, and n equal 2 case, 6 loop theory is divergent at 6 loop. N equal 1 case, I'm not sure at what loop, probably in lower loop, theory will be divergent. But if you look at the, say, effective low energy theory in Coulomb phase, where you have this abelian theories scattering each other, between photons are scattered each other. And then there is a contribution from W bosons and instantons and all these perturbative and non-perturbative corrections, such a way that, because theory is well defined, this amplitude should be finite. And we don't have any good algorithm for that. I mean, there are a lot of directions one could pursue, but there's no no way we know. And so this looks like to me very challenging question. How to make it's like a string theory. If you look at the low energy effective theory like Yang-Mills supergravities or supergravity theory, then it's UV incomplete, and the string theory makes it finite. But in string theory, we have a weak coupling constant, and we can do string perturbation. But this theory is not weakly coupled at all. It's infinity. Coupling constant is infinite. So when you go to the, say, Coulomb phase, even for SU2 theory without any flavors, you go to low energy, then you do photon scatterings, and then there is all kind of effect that has to be included. And I don't think anybody have explored that direction. So to me, that seems to be one of the key challenges of the theory. And then there are geometries, there are classification and dualities, there's a higher rank, degrees of freedom. For example, there's a list of the rank 2 theories. You would ask, what's the say F maximization? Which one is the lowest degrees of freedom? That sort of questions. Depending on Chern-Simons levels, how do you identify that? And I don't think people have come up with that answer either. And then I mentioned briefly about relation to 6D theories, but it also has a relation with 4D and 3D, and people have been exploring that direction fruitfully, but people haven't done much of, and I think it still is at the beginning stage. And also, I didn't have time for that, but this 5D theories has some relevance to little string theories in 6D, which is a mysterious class of theories. So in 6D, you can have string theory where you don't have gravities, and this little string theory strings are interacting very strongly, so you don't have a string perturbation. And these theories are again very interesting, as much as interesting as the superconformal field theory in 60. And I think still we're at the beginning stage of the game. Okay, let me finish. Thank you.
Questions?
So let's say that I had a pre-potential with some
Right.
mass parameters in it and
Right.
coupling